Hello friends, welcome to the thermal and optical properties of polymer testing and the edges of the polymer process engineering. In the previous lecture, we covered about the tier, the test piece geometries, standard methods. We discussed about the fracture toughness. In this aspect, we discussed about the fundamental concepts of fracture toughness. Then we discussed about the various testing methods like ASTM, BES and ISO. In this particular segment, we are going to discuss about the physical properties, the thermal properties like heat conductivity and diffusivity. We will discuss about the differential scanning, calorimetric, DSC, thermogravimetric analysis like TGA, thermomechanical analysis, TMA. Apart from this, we will discuss about the optical properties like refractive index, refractometer, polarization, optical testing. So, all this we are going to cover in this particular segment. So, let us start with the thermal properties. See, the macromolecular structure of polymers and the resulting bonding relationship, they have a significant role in determining their thermal characteristics. The chemical and physical makeup of the polymer affects the movement of atoms, segments of molecules that are subjected to thermal energy. Now, due to increased motion of atom, side chains and a molecule segment after being subjected to heat, the proportion of secondary valence bond reduces the thermoplastic material. So, in contrast, the thermoset, the molecule's ability is governed by its 3D network. The head application causes the softening but not melting, and the primary valence bond in the network, they are broken away during the decomposition process. Now, additionally, the movement of the molecules and the component of the molecule was related to the mechanical properties, and therefore it is particularly important to determine the polymer's thermal characteristics. The physical and chemical properties are measured using the thermal analysis technique as a function of temperature and time. In dedicated ovens with the specified gas temperature like inert gas or air, the specimens, they are subjected to the defined temperature programs. In order to determine the material's glass transition temperature, melting enthalpies, temperature ranges of the secondary relaxation regions, thermal degradation and degree of crystallinity, corresponding heating or cooling curves that exhibits the material's specific dependencies are recorded. The thermal analysis technique can be used to carry out the different analysis like structural change, the phase transition, the glass transition, melting, crystallization, cross-linking, volatilization, sublimation, etc. And the mechanical properties like damping and elastic behavior, the thermal properties like specific heat capacity, melting, crystallization, temperature, coefficient of expansion and expansion, shrinkage, etc. The chemical reaction in solution or liquid phase, thermal stability and decomposition in various gaseous conditions likewise. Now, the thermal analysis method, this includes the differential scanning calorimetry, thermogravimetric analysis, thermomechanical analysis, dynamic mechanical thermal analysis and thermo-optical analysis. So, before we go into the detail, let us talk about the heat conductivity. The typically elastic waves in a solid body, these can be used to transmit heat in polymers, and energy exchange occurs when molecular segments collide. The heat conductivity, which can be thought of as a quaternized transfer process occurring at a sound velocity, this is measurement of the energy transmission in material. The relationship expressed by dB and which is given like this. Here the Cp is the specific heat capacity, rho is the density, C is the sound velocity and L is the distance between the molecules, and lambda is the coefficient of thermal conductivity. The heat conductivity or the coefficient of thermal conductivity has a physical unit of watt per meter Kelvin. The basic equation for heat conducting process is Q over T, that is equal to minus lambda A naught del T over del X, where Q is the amount of heat, T is the time, lambda is the heat conductivity, T is the temperature, X is the length of the direction of heat transfer, A naught is the area of the cross section object and minus sign indicates that heat flows in opposite direction of the temperature gradient. The equation of the heat conduction, this can be derived from the differences between the heat entering and exiting the volume element, that is A naught dx. So it can be represented as dq1 minus dq2, that is equal to lambda A naught del 2t over del x2 dt. For unsteady state, dt over del t over del x is not equal to 0. So we obtain a complete equation of thermal conduction by taking into account of all three spatial dimension. So it can be represented as del t over del t lambda over Cp rho del 2t over del x2 plus del 2t over del y2 plus del 2t over del z2. Now the quantity lambda c over Cp rho is thermal diffusivity alpha. So for steady state, del t over del x is equal to 0. Then on solving this equation, we have the q over t is equal to lambda A naught T1 minus T2 over x. The heat penetration coefficient B, this can be defined as B is equal to square root of C lambda rho. Now for determining the contact temperature Tk, the Tk is equal to BATA plus BBTB over BA plus BB, where BAB, the heat penetration coefficient, and TAB is the temperature at surface of body A or B. Now, this is the basic protocol for or schematic diagram for showing the working principle of measuring thermal diffusivity by the laser flash method. Now, here this is the specimen is heated on one side while the other side is used to measure the result. The thermal diffusivity can be measured with this particular technique throughout a temperature range of minus 40 degrees Celsius to 2000 degrees Celsius. Here you can see that there is an IR sensor. This is the furnace for heating, and you can subject the specimen over here. This is the laser gun or laser power supply. Apart from this, these are the units where you can record the things or data. Now on a specimen's bottom side, the heat impulse is produced, and on its top the IR sensor detects the rise in the temperature, and the time dependent temperature change can be used to calculate the thermal diffusivity. So the relationship this produce the heat conductivity can be given as lambda is equal to A rho Cp, where A is thermal diffusivity, rho is the density, and Cp is the specific heat. Now, when measuring the thermal diffusivity or using a DSC, a specific heat Cp is determined by comparing the temperature curve of the specimen to that of a known specific heat reference material. Let's talk about the differential scanning calorimetry, DSC. The heat flux calorimetry and the power compensation calorimetry are the two fundamental measuring principles that guide the design of a DSC devices. According to a chosen linear temperature program, two bean sized pan tray dishes, and each containing a sample and an inert reference. They are heated concurrently, and the reference is frequently used to be air. This is the typical figure. Now, with the help of the additional temperature sensor which gauges the oven's baseline temperature, thermal asymmetrics can be corrected in the oven more effectively. The following formula which we are going to write, this can be used to determine the enthalpy and the specific heat as a function of a temperature, like dq is equal to mcp T dt, and q is equal to m delta h is equal to m T1 to T2 integration, then Cpt dt. Now, here Q is the heat quantity, m is the mass of sample, T is the temperature, Cp is the specific heat capacity, and H is the enthalpy. Now, if we talk about the phase transition, the specific heat capacity and the enthalpy curves, they shift characteristically with the temperature, and the dependence of specific heat capacity on temperature rises sharply in a glass transition zone, that is in the left, while the melting range peaks is there, that is on the right. Now, the glass transition measurement, the relationship of specific heat capacity on temperature is based on ISO 11357, and semi-crystalline polymer have a comparatively large melting range compared to the metallic material. The temperature and mechanical history of the polymer material has a significant bearing on material and consequently the melting curve. So, the temperature Tm of the endothermic peak in the dependency Cp is a function of temperature, and the dq over dt over m is a function of temperature, is referred to as the melting point for polymer, and is the temperature at which the majority of crystallities melt. The identification of the polymer for the quality control is one of the key application of DSC. In most cases, this is accomplished using the transition temperature, that is a glass transition for the amorphous polymer, and glass melting temperature for the semi-crystalline polymers. Let's talk about the temperature modulated DSC, or sometimes referred as a TMDSC. This technique can be used to separate the non-reverse processes like cross-linking, breakdown, and evaporation from reverse processes like glass transition and melting. A reverse and non-reverse heat flow, they are separated from the overall heat flow signal according to the standard DSC measurement. Repeated heating can produce the reverse component, which depends on heating rate, heat capacity, and other factors. Now, it is impossible to duplicate the finished non-reverse component. The sample is periodically heated using either sinusoidal, triangular, or sawtooth modulation, which is the key distinction from the conventional measuring approach using a linear heating rate. In circumstances when there are superimposed effect, the TMDSC is a crucial aid. Now, in this particular figure, this you can see the use of temperature modulated DSC for characterizing bitumen. The non-reverse heat flow has a rather complicated curve in the temperature range of -50 to 90 degrees Celsius. The energy needed to release the degree of alignment created during the cooling in the individual bitumen segments is referred to as an endothermic background, and it spans the temperature range specified. Now, the cold crystallization of a low molecular saturated hydrocarbon at around 5 degrees Celsius and the cold crystallization of high molecular saturated segment at roughly 25 degrees Celsius superimpose this particular process. The release of asphalts and resin into the alignment, as well as the melting of previously cold crystallized high molecular weight saturation segments, cause the endothermic peak at about 40 degrees Celsius. Now, oxidation induction time or temperature sometimes. By calculating the oxidation induction time, DSC can also be used to compare and assess the resistance of polymer to thermo-oxidative degradation. The so-called static approach is a dynamic one with a relatively low sensitivity where DSC measurements are made in an oxygen or air-filled environment at a temperature where the exothermic oxidation is being detected, wherein the sample is heated in presence of an inert gas to a specific temperature that is higher than Tm. When equilibrium has been reached, this temperature is maintained and the environment is changed to an oxidative one. And this method involves timing the oxidation reaction to happen, and the ASTM D3895 standardized the statistical OIT approach. Now, this particular figure shows the impact of oven aging on the oxidative induction time, which was determined using the POM homopolymer pellets at 190 degrees Celsius and 3.4 megapascal of pressure. Let's talk about the thermogravimetric analysis, a tool for measuring mass changes in a sample as a function of time and temperature is provided by the thermogravimetric analysis. Evaporation, decomposition, chemical reaction, magnetic or electrical transition and other processes all result in mass changes. When gases such as oxygen, humidity, etc., they are absorbed, there is also quantifiable mass change. ISO 11358 standardizes this particular process. Now, combining it with the mass spectroscopy or FTIR as per this particular figure, this gives a tool to identify the substances that are responsible for a specific mass loss, which can be useful for solving polymer analytical issues. Now, various purge gases, they are employed depending on the measurement requirement to record mass change as a function of temperature or time as per this particular figure. For the interpretation and a separation effect, the differential measurement signal, they are also known as DTG curve, is frequently introduced, and additional detail on the kinetics of deterioration, they are provided by the DTG signals. So, at about 300 degrees Celsius, the first decomposition, now here you see that around 300 degrees Celsius, the first decomposition maximum happens. Now, plasticizer and low molecular segments volatilize in the temperature range up to say 400 degrees Celsius, and the polymer parts of EPDM decompose at temperature between 400 to 500 degrees Celsius. The atmosphere is changed from nitrogen to oxygen at 600 degrees Celsius, which causes the carbon black to burn off. Ash is the residue that is left behind. Let's talk about the thermomechanical analysis. As the temperature rises, polymers expands because of unentanglement of the chain. The average linear alpha, that is also known as a thermal expansion number or the cubic or a beta coefficient of thermal expansion of the specific material, is revealed by measuring thermal expansions together with significant transitional effects during heating. When a body's length, say L1, or a volume V1 change with the temperature increase of say 1 Kelvin, the term thermal expansion coefficient K inverse is used. When only a small temperature range is considered, the resulting length change can be given by this particular formula, that is L1 is equal to alpha L naught T1 minus T2. Now, for three-dimensional expansion, V1 is equal to beta V naught T1 minus T naught, the isotropic body, beta is equal to 3 alpha. However, since the coefficient alpha and beta are temperature dependent, non-linear dependency are to be expected. So, alpha is equal to 1 over L naught del L over del T at constant P. Respectively, beta is equal to 1 over V naught del over del V over del T at constant P. Now, the secondary relaxation which occurs as temperature rises causes local motion of tiny groups of molecules, and the primary relaxation which follows cause the cooperative motion of entire molecule segment. Now, in the transition ranges, the thermal expansion coefficient fluctuates irregularly. A reliable method for figuring out the linear thermal expansion coefficient of the polymer is thermomechanical analysis, or TMA. Unlike non-containing dilatometry, TMA measurement make use of a steady light applied load. It is common to utilize a cylindrical or a rectangular specimen with plain parallel measurement surfaces. A quartz punch is used to apply a small load of say 0.1 to 5 gram, and an inductive measuring device is used to detect the thermal expansion at the same time. The test is set up in oven that is being heated slowly. So either an average coefficient of thermal expansion, that is alpha T, or a differential coefficient of thermal expansion alpha can be calculated using ISO 11359. So this can be written as 1 over L naught L2 minus L1 over T2 minus T1, 1 over L naught delta L over delta T, and alpha T is equal to 1 over L naught dl over dt. So the increase in the tangent at the dependence delta L over L naught yields the differential coefficient of thermal expansion, and it is always not when the experiments begin. The first heating cycle in the TMA always delivers data on the thermal and mechanical history, much like with the DSC. Now, heating has the potential to induce the post-crystallization, release orientation, and a residual tension in addition to evaporation. These all result in shrinking and prevent thermal expansions. In thermosets, post-curing has the same effect, and injection molded and extruded parts must also take anisotropy effect into account, and this is true for the filled and reinforced materials. A more or less dramatic contraction occurs in heated semicrystalline polymers, and the linear expansion coefficient in the molecular direction, this can take on negative values, and this is due to the tie molecules undisturbed return on their amorphous ranges in the rubber elastic state. Since the volume measurement yields positive value, the expansion coefficient perpendicular to the direction of orientation must also strongly rise, since the volumetric measurement yields positive values. The coefficient of thermal expansion depends on contribution of the components and phase compatibility in amorphous multiphase system, which are comparable to semicrystalline polymers. The expansion coefficient often adheres to the straightforward additive rule when both components are above glass transition temperature. In region between the transition temperature of the relevant polymer, this is the only partially true. Since matrix material expands to a greater extent than the filler, the polymer composites with inorganic filler often display lower thermal expansion induced by filler quantity, particle shape, and the process dependent degree of alignment. Now, as a result, the anticipated internal stresses are stronger, particularly at the polymer filler interface. The expansion coefficient of a composite can only be analyzed to a limited extent using the laws of mixture. This particular figure demonstrates how fiber reinforce affects circular plate thermal expansion. A significantly higher thermal expansion occurs in the direction of a thickness which is mostly controlled by the thermal expansion behavior of the unreinforced matrix, as opposed to the slight changes in the thermal expansion behavior that are observed in the radial and tangential direction. The anisotropy of the thermal expansion behavior allows for interface about fiber. Now, let us talk about the optical properties. The plastic optical properties tests are necessary for both product aesthetic and characterizing the polymers and molded part made from them. The product's market value is significantly influenced by its surface features. Among the critical optical characteristic value of opaque or transparent molded parts are color, gloss, and surface texture. So, basic basic optical principle including reflection, refraction, dispersion, diffraction, interference and polarization provide the basis for some test involving the optical properties of the plastic. Now, in this, the refractive index determination plays a very vital role. So, when light travels non-perpendicularly from one medium into another with a variable refractive index, it also changes direction. The constant n in the ratio of the sine of the angle of incidence to the sine of the angle of diffraction, which also known as the refractive index and diffraction index or diffraction quotient, and describe the substance that passed through. Now, there are several laws of diffraction which is applicable in the light ray passes through an interface of two media with the diffraction indices n and n prime. Now, on diffracting the product of n sine this remains constant, is known as a Bayes invariant. Now, refractive index determination, the temperature controlled two prism Abbe refractometer is an excellent choice of evaluating polymers. A thin lamella is positioned between the prism with one serving at the lighting prism and other as the measurement prism in order to calculate the refractive index of liquid. So, at a measurement temperature of 20 degrees Celsius, illumination is given by monochromatic light from sodium vapor lamp. Now, on the device, the dispersion edge that appears at the black to white transition many typically be removed. The black white transition of the total reflection is established in one speed eyepiece by angling the prism pair against the illumination beam as per this particular figure. Now, only one flat surface of a solid material roughly the size of the measuring prism needs to be polished. On the measuring prism, this particular plane is placed within an immersed liquid and the liquid must not damage the interacting material and have a refractive index that is greater than that of the specimen but less than that of the prism, and the direction of light incidence is indicated, this is by an arrow. Let us talk about the polarization. The transfer waves have the ability to polarize when they are in particular perfect oscillation condition. In this case, the propagation direction is perpendicular to the oscillating value, the light or a field strength curve vector. Non-polarized light, this light vector is perpendicular to the propagation direction in all conceivable directions. However, when the light is polarized, the vector at every point in space adopts a parallel position to a clearly defined direction, and polarization direction refers to this particular optimum oscillation direction. So, when the oscillation directions of two polarized light waves are perpendicular to one another, the overlapping does not result in intensity interference, but rather a change in the oscillation state of the polarized wave. The phase difference between the two polarized waves amplitude determine how the resulting field vector moves. So, the linear polarized light is produced by overlapping when the phase difference is 0 or 180 degree, and elliptically polarized light in all other situations. When we talk about the polarization optical testing methods, the measuring of a mechanical stress in a polarimeter is come into existence. This cast isotropically are the transparent model bodies made material like epoxy resin or PMMA, and in an upper loaded state they then mostly appear black between crossed polarizer. In a polarimeter, the specimens are loaded in a way that is adequate for practical use, and resulting optical stress difference is measured and recorded digitally. And then the assessment of stress and deformation under both static and dynamic loading can be carried out. This figure displays the stress optical recording of the model body to distinguish between the colored and black isochromatic lines, and the network of isoclinic lines can be geometrically translated into an isotactic line network which depicts the progression of the main stresses in the model body. And the polarizer and analyzer, they are quickly rotated in the relation to the model body to separate the isochromatic and isoclinics, and thereby the isoclinic network travels and can no longer be seen by the naked eye at high velocities. So, in the illustration, only the stationary isochromatic image remains visible. Now, to eliminate the isochromatics, a polymer such as PMMA is used that has a stress optical constant as low as possible. Now, despite high loading, only isoclinic appears, and to perform such a stress optical test, the literature should be consulted. Without determining the absolute numerical stress value, the stress optical image permit the recognition of the direction of the principal stress and low stress region as well as the area of local stress concentration. So, dear friends, the outset we discussed the various test protocols with the thermal as well as the optical one, and for your convenience we have enlisted several references which you can utilize if needed. Thank you very much.